Hi, and welcome to the AMIA Clinical Informatics Board Review course. This is Lecture 3A1, Computer Programming and Methods of Software Development, and I'm Bimal Desai, your lecturer for today. Here's the core content that we're covering in this lecture. It's Section 3.1.1, Computer Systems. And there's quite a bit to cover here. We're going to cover some basics of computer programming, data and control structures, software development methodology, system integration, and quality testing. And here's a lot more detail of the key topics we'll be covering. So let's start all the way at the beginning with how computers actually represent data. As all of you know, computers represent data in binary, which is base 2 math. You can think of a single binary digit as being either a 0 or a 1. And this is very convenient for computers because they can store electrical impulses or signals as on and off. The text that we see on a screen in a computer is actually encoded in something called ASCII as one of the encoding standards for various character systems. And a typical ASCII letter can be represented as an 8-digit or what we call an 8-bit binary code. And this is specified by an ISO standard, ISO 8859-1 or ISO Latin 1. Now, if you've looked at the ASCII spec in any detail, you'll see that it's comprehensive for most of the languages that use the Roman alphabet, but it doesn't really cover the other languages of the world that include things like Cyrillic and Hindi and other alphabets. And if you're only using an 8-bit character encoding schema, you'll quickly run out of space. In other words, with an 8-bit binary digit, you can't possibly have a namespace that covers all of the different possible characters in all of the different human languages. So for that, they've developed a new standard called Unicode, which is actually 16-bit, and this allows encoding of most of the world's languages. And 16-bit characters are actually exponentially larger than 8-bit characters in terms of the largest number you can represent, and that's why you can fit so many more possible human language characters into Unicode than you can in 8-bit. Because 16 is a power of 2, you can actually represent binary digits in hexadecimal or base 16. And as an example of how you can translate back and forth and how people might be able to condense information, think of the word informatics represented in ASCII characters, just the lowercase letters INFORMATICS. Each of those has an 8-bit binary digit assigned to it in the ASCII encoding schema. And those 8-bit characters, again, can be represented as a 2-digit hexadecimal character. So the string informatics is represented by the hexadecimal string shown in red there. And each one of those characters, so for example, the number 69 in hexadecimal is the exact same as the binary 8-bit character 011010001. And you can see that it's a lot longer. It takes a lot more space to represent these strings in binary, but we're talking about billions and billions of bits or bytes of data, and so computers are very efficient at storing these, and therefore it's actually a very convenient way to store these data. Just a bit of terminology. The word bit is a contraction of the words binary and digit, and a bit is also a very convenient way for representing different logical functions like true or false or Boolean operators, as well as algebraic information like positive or negative. By convention, a byte is actually an 8-bit character string. So a single byte of memory, for example, is sufficient to represent a single ASCII character. Now let's talk about how we get from these single bits of data, these billions and billions of zeros and ones, to actual computation. And for that, we have to go all the way back to George Boole, who was an English mathematician and a logician, and he lends his name to Boolean algebra or Boolean operators. So George Boole envisioned that you could actually do math with these simple operations that he defined. For example, the conjunction operator, which we think of as the word and, the disjunction operator, which we think of as the or operation, and the negation operator, which we think of as not. All of these have their own notation in various computer programming languages. The most common ones you see for and, for example, in JavaScript and Java, and is represented with an ampersand. The or operator is often represented with either the word or the two vertical pipes. And the negation operator is often represented with the word not or an exclamation point, oddly enough. So if you see an exclamation point in a computer programming language, it usually means not. Another way to think of what these Boolean operations do is to recall that they also can be used when we talk about Venn diagrams. So imagine two intersecting circles. There's A and B, and then there's an area where they both overlap. For the phrase A and B to be true, the only items that would satisfy that are things that are both in the circle represented by A and in the circle represented by B. So the conjunction operator, the and operation, is actually the intersection of those two. When we think about this from the standpoint of binary numbers, if you imagine that logic gate on the right, and this is another convention that we'll talk about in some detail, George Boole imagined two inputs going into a logic gate, one that would give you the value of A and one that would give you the value of B. And the AND operation would only return true if both A was true and if B was true. If either one of those was false, then the logic gate diagram on the output side, that right little stick, would also return false. The disjunction operation in Venn diagrams can be thought of as the union of two different sets. So, for example, all of A and all of B. If it doesn't matter if anything is in B, if any item that's in A or any item that's in B would allow that statement to be true, the phrase A or B. And again, in the logic gate diagram, represented by that kind of pointy arrowhead thing, if you have an input A and an input B, the output of that logic gate would also be true as long as at least A or B is true. So if A is true, is B is true, or if both are true, then the output of that will be true. The only time that would be false is if both are false. The negation operator in Venn diagram language is basically the opposite, the not, the negative of whatever set you're talking about. So if A is coming in, then not A is the exact opposite. And in the logic gate version of that, represented by a triangle with a circle on the end of it, if A is true, then the output is false. If A is false, then the output is true. It literally flips the input of what comes in and returns that as the output. So you might be thinking from that example, well, what is a logic gate? And at the time, George Boole probably only had access to mechanical versions of these. If you look on YouTube, you can actually see people building like marble courses that can mimic some of the mechanically mimic a logic gate. But we now have digital circuits that can do this Boolean algebra, that can take two different inputs in A and a B and either return a true or false. In other words, if it senses an electrical impulse at A or an electrical impulse at B, then it might pass on an electrical impulse at the other end of the logic gate. And in addition to the three, the and, or, and negation, there's a few others that become important. One is called the exclusive or XOR, which is the bottom left one here. This one is interesting because unlike the usual OR, where either A or B or both can be true, exclusive OR will only return true if exactly one of those two inputs is true, if either A or B is true, but not both. And that's what the exclusive part means. They can't both be true. In fact, if A was true and B was true, then the exclusive OR gate would return false. The next gate that Boole described was this thing called the not and operator, or the not and gate, often abbreviated as NAND, N-A-N-D. And this one will return true unless both A and B are true. So the easiest way to think of this one is that it's the opposite of the and. whereas the normal AND operator, if A was true and B was true, would return true. This one, when A is true and B is true, returns false. In every other circumstance, it will return true. And the third odd one is this one, not or the NOR operator. And it returns true only when both A and B are false. And again, the easiest way to think of this one is to take what would normally go through an OR operator and negate it, or flip the output. At this point, you're probably tired of looking at these logic gates, but I promise you that there's a good reason to think about what these represent. As a simple example, imagine we were building a circuit with these two logic gates. It has two inputs labeled A and B, and it has two outputs labeled S and C. A and B both get passed to an exclusive OR gate, and the output is S. A and B also, the inputs get split off and set to an AND gate, and the output is C. Now, if I want to see what this gate does under a variety of circumstances, different values for A and B, the easiest way for me to keep track of these outputs is to do something called a truth table. And that's what's shown here on the right. You can see that I've listed a column for A, a column for B, a column for C, and a column for S. And basically what I do is I enumerate all of the different options, all the different permutations of A and B. And there's four of them there. There's the situation where A is true and B is true, represented by a 1. There's a situation where A is true but B is false, represented by a 1 and a 0. There's a situation where A is false and B is true, represented by a 0, 1. And the situation where both inputs are false, represented by 0, 0. And if you follow the column for C, you'll recall that the AND gate only returns true when both A and B are true. So that's why in that first cell in column C, A and B is true, because that's the only time when both A and B are true. And in every other cell below that, you can see that it returns false or 0. If we do the same thing for column S and try to fill in the 1s and 0s, what we see is that both the top and the bottom options, where A and B are both true and when A and B are both false, returns false. And by definition, the exclusive OR gate only returns true when exactly one of those two inputs is true. So the situation where A is true and B is false, or where A is false and B is true. Okay, so now we filled out the truth table. And what Boole and others stumbled upon was that, hey, look, we're actually doing binary math when we do this. When we line up these logic gates in this way, remember that in binary, 1 plus 1 equals 1, 0. Please don't read that as 1 plus 1 equals 10. That's binary for 1 plus 1 equals 1, 0. And George Boole looked at his little 2 logic gate circuit and realized that when A is 1 and B is 1, C is 1 and S is 0, just like the numerals 1 and 0 in binary math. And in the situation where A is 1 and B is 0, C is 0 and S is 1. So 1 plus 0 in binary math equals 0, 1. Similarly, 0 plus 1 in binary math equals 0, 1, and 0 plus 0 equals 0, 0. So lo and behold, we've created a simple logic gate circuit that can actually do 2-bit binary math. And this circuit is something that's called a half adder. Of course, there are many more complicated versions of this. There's a version that there's a full adder. There's circuits that can do multiplication and division and subtraction and all kinds of stuff. And they're all composed of these tiny little logic gates, which again, George Boole could not even, there was no digital version of these back when he invented this. These were all sort of conceptual, mathematical concepts. So recall that when George Boole invented Boolean math, there was no sort of electronic or digital manifestation of these. You couldn't build a logic gate electronically. There were probably physical things, like I mentioned, the marble runs and other mechanical contraptions. By the 1940s, people had figured out how to make these logic gates using vacuum tubes, which is why the first computers, like the computers used for in Bletchley Park in England to break the Enigma code, basically used giant rooms full of vacuum tubes. But in 1947, something remarkable happened, which was that the transistor was invented. And a transistor is a tiny electronic device that uses silicon semiconductors. A semiconductor is a material that can either conduct electricity or resist the conduction of electricity based on some other external electrical input. So basically, you can use these as tiny, microscopic little electronic switches. Under the influence of a current, it can either conduct or resist electricity. And if you line up these semiconductors in a very specific way, if you line up these transistors in a very specific way, you can actually build physical logic gates. So a single logic gate, like one of these exclusive or not and gates, might need something like 20 transistors. And these days, we pack these transistors along with resistors and diodes and capacitors onto prepackaged circuit boards called integrated circuits, or ICs. And we've also miniaturized these orders of magnitude smaller than back in the 40s and 50s. So your smartphone, for example, contains 100 million transistors, and your PC has over 1 billion. And each one of these is only 22 nanometers wide at this point. Now, there's something called Moore's Law, which predicts that the number of transistors on an integrated circuit will double every 2 years. And this is held up to be very true. In fact, people are predicting that at some point we'll get to a scale, an atomic scale, where it's going to be too small to pack more and more transistors onto an IC. But there are still some tricks that the chip manufacturers have to continue this trend, like going into 3 dimensions instead of flat integrated circuits, but packing them into sort of 3-dimensional structures. So here's, again, the definition of Moore's Law, which predicts that the number of transistors on an IC will double every 2 years. And again, because transistors represent computational capacity, the number of logic gates, the number of mathematical functions you can perform, it predicts that the speed of a computer will double every 2 years also. And this has held up remarkably well between 1971 and 2011, as shown in this graph here, that the number of transistors has completely and almost precisely followed Moore's Law. These days, these processors can do billions of calculations per second, and they're so fast that we now count the number of mathematical operations in this unit of measure called a flop, which stands for a floating point operation. And so the number of flops per second is the number of floating point operations per second that a computer can do. And a gigaflop is 1 billion floating point operations. And this is the statistic that should blow your mind. It absolutely blew my mind, that a gigaflop today is 100 trillion times cheaper than it was 50 years ago. In other words, to build a computer that can perform a gigaflop of calculations per second, is 100 trillion times cheaper, adjusted for inflation. So back in 1961, the first computer that could perform a gigaflop operation was this IBM 1620 unit, and you needed 17 million of them at a cost of $64,000 each. And today, at least as of the summer of 2017, you could buy an AMD chip that could do this for about 6 cents. The remarkable thing to me is that if you look back in June 2013, we hit the gigaflop barrier with the Sony PlayStation 4 at only 22 cents, less than a quarter per gigaflop. So computation these days is remarkably cheap, and you can pack these incredibly powerful computers into very, very small spaces, into tiny objects for very low cost. So that's how computers do math, and that's how they do it fast. Now the question is, how do you instruct a computer to do something useful? And this is where we have to get into programming languages, and we're going to spend the bulk of this lecture talking about this. At the level of the central processing unit, the CPU of a computer, the architecture, the layout of those integrated circuits, how all of those transistors are arranged and how they pass information back to one another is unique to the manufacturer. And when you're trying to represent instruction sets for very specific types of CPUs, these are basically done at the level of what's called machine code. Machine code is basically binary instructions, and these were never intended to be human interpretable, but this is at the level of how bits and bytes are passed around. They're passing machine code instructions back and forth. And because the these layouts, these different manufacturers have different standards. This is why when you compile code for one type of processor, like an x86 or an Intel processor or a Spark processor, they're often incompatible with other types of processors. And this is for years why code that was written for Macs didn't run on Windows, and actually that's still true, but even though they're similar processors these days. A typical piece of machine code might look like either a binary or a hexadecimal notation, like that example there, where you might maybe in the hexadecimal codes B061 means something to the actual processor. But of course, humans can't efficiently program in binary or hexadecimal, so they created something called assembly language, and assembly language was the first attempt to make fairly human readable but very concise instructions for a computer to interpret and execute at the level of machine code. So think of these as kind of short mnemonics. They're still tedious to use. They're not exactly readable like some of the higher level programming languages, but they get the job done. So for example, the instruction MOV AL, 61H might be an assembly language shortcut or shorthand to instruct the computer to move the contents from one memory register to another location in the working memory of the computer. Thankfully for all of us, computer programming languages have evolved to the point where most of these are written in English-like phrases. We call these high-level programming languages. Because they're written in English and because the processors don't understand English, you have to go through a step of compilation. So this code is compiled before it can be executed. And that compilation step basically converts your human language code into assembly language or machine code. And again, that's why the compiler has to be unique to the processor also, that the way you compile Java to run on a Mac might be different than the way you compile Java to run on Linux or the way you compile Java to work on a Windows machine. But as long as you can write Java, and as long as you have the compiler for each of those operating systems, you can run Java on multiple platforms. So an example of what compilation does. Examples of high-level programming languages are, for example, C and C++, or Java, or Visual Basic. And one level higher from these is something called the fourth generation languages, where you've further abstracted complex or repetitive or very stereotyped tasks. And so, for example, maybe these are computer languages that are specifically tuned to generate reports or to create data visualizations or to interact with the database. Oftentimes, these are very task or domain specific. So you can think of some of the statistical tools like SPSS and the command line instructions that you would type into that as fourth generation programming languages. Same thing for very specialized languages like Mathematica. So how do you program a computer? Well, first of all, you have to choose what's called a programming paradigm. The way you organize your code typically falls into a couple of buckets: imperative/procedural, and something called object-oriented. And we'll go through both, and they're quite different. And the choice of this programming paradigm is really what influences the performance of your code, how maintainable it is, how long the code is, the memory requirements, and so on. So here's some examples of imperative and procedural programming languages. You're probably familiar with some of these, like Fortran, BASIC, Pascal, C, and C++. And in each of these languages, programs are basically a list of tasks and subroutines, and they're performed stepwise, like a recipe almost. Because there are some procedures you would do over and over again, they've created often ways that you can define functions or subroutines that you can reuse throughout the program. But for the most part, there's sort of a linear flow, and you can either jump back and forth within the program and then return back to where you are with different statements. So that's sort of one style of programming. In contrast to that, there's a paradigm called object-oriented programming. Examples of these are Java, Objective-C, Visual Basic.NET, and many others. And in object-oriented programming, if you haven't encountered these before, it takes a little bit to get your mind around these. Programs are basically constructed as a collection of interacting software objects. And you might be thinking, well, what the heck does that mean? So we have to kind of back up a little bit and talk about this, that an object in the software sense is a piece of code that can have independent functions, it can have different characteristics, it can occupy different states. And when you create an object, you first have to define what the blueprint for that object is. So for example, and this blueprint is called a class. The class describes the functions and characteristics that all members of that object have in common. So let's say, for example, I wanted to write a computer program that had something to do with dogs. I might first define the class of all dogs. Let's say it's a veterinary tracking system or something like that. So I need to be able to represent a dog somewhere in this software system. So I might create a blueprint for what represents a dog and what dogs can do and the characteristics they possess, the attributes they have. And then when I want to create a specific dog to use or to store in my system, I would create what's called an instance of that class. And now by creating that instance, I've made a sort of a physical version, or a software version of that object. So I might have the class of all dogs, but in my veterinary information system, if a beagle gets registered in my clinic, then a beagle might generate an instance of that dog class. To continue this analogy, objects can have what are called attributes, which you can think of as the adjectives that describe the object. So the beagle might have a name, it might have a fur color, it might have an owner, it might have an age, it might have a sex. And objects can also have methods, which you can think of as the verbs. So at least in a veterinary system, the beagle might be registered, the beagle might be deceased. There are different things you can do to the beagle. You can schedule it for a procedure or whatever that might represent these verbs. If it's really just a dog and you want the dog to do something, the verbs might be things like barking and running and rolling around. There is this funny word called instantiation, which is the act of creating an instance of an object or a member of a class. And when you instantiate an object, that's when you set the initial parameters. That's when you first define, okay, here's the values for the different attributes, and here's the methods that this new instance of the class can actually perform. And as I mentioned before, imagine we have this class of dog, and then it has attributes for fur color and name and breed, and it might have methods for barking and rolling over. And when I create the instance of the class, I can actually populate the fur color with a specific color. I can populate the name with a specific name and the breed with a specific breed, and so on. Classes can demonstrate something called encapsulation. And encapsulation is the idea that the class can be defined in such a way that not all of the attributes or methods can be accessed by outside objects. In other words, the class has the ability to control the access, whether it's the invocation of those methods or the modification of those attributes. And this becomes very vital in object-oriented programming. Another note about these slides, all of the terms that are in bold are special definitions that are unique to object-oriented programming and that are eminently testable. Continuing the object-oriented programming terminology, there's this term composition, which is the notion that objects can be composed from smaller objects. And this is actually probably one of the most powerful things about object-oriented programming, that you can create very complex software objects from smaller, simpler objects. So for example, imagine that I'm creating a system that's supposed to draw a line on the screen, but elsewhere in the system, or previously in the system, I've defined a way to represent an XY coordinate, a single point. Once I've defined that point object, or the class of XY coordinate points, I can simply use those to create a class for a line, and I don't have to redefine it when I create the line class. I can simply compose it from the base classes. Classes can also exhibit something called inheritance. Inheritance is the notion that objects can inherit their structure from parent objects and then extend their functionality. So just like human children, they take after their parents, but then they often surpass them. Imagine we have a human resources system where we need to represent classes, distinct classes for the things, the attributes and methods that are unique to managers and the attributes and methods that are unique to other staff. They may both share some attributes and methods in common that are represented by a parent class called employee. So we can inherit all of the useful stuff from employee and override it when we need to extend it to create the manager and the staff classes. In fact, the way you override it is this idea of polymorphism. So polymorphism is the idea that objects can override their parent attributes and methods, the details of how you implement that subclass will determine which attribute and method is invoked. So the example I give here is that imagine you have the class of animals and they have a generic method for making a noise. The subclasses of animals, the derived or child classes of animals, might be various types of animals like dogs and cats and mice. And they may have a make noise method that they can implement totally differently, or they can override it, or they can omit it entirely. There's the methods for a class generally break down into two useful types, at least the ones that are used to modify the attributes. They're called accessors, which can get the value of an attribute, and these are often in computer slang, programmer slang, called getters. And there's mutators, which are used to change the value of a variable or an attribute. And these are often called setters. So you've got your getters and your setters, or your typical methods. And this is so common that when you sort of, in many of the software development environments, when you create a new class, it'll kind of give you a scaffolding for like, okay, here's where you put all your attributes, here's where your methods are, here's where you define your getters, here's where you define your setters. And I've followed that sort of scaffolding here. So this is an example class. The details of which language this is and stuff are not that important. They're not going to expect you to know a specific object-oriented programming class, but this one happens to be in Java. And the very first thing I do when I define the class is I have to declare whether it's a public or a private class. In other words, are other parts of the software system allowed to use this class or not? In this case, it is. I'm saying that it's a public class called dog, and it extends a base class called mammal. And in green there, I've listed all of the strings, the attributes. So I'm listing my attributes up front. Notice that these are all private, which gets at an important facet that there's a private string that we're going to store the value of the dog's name, another string for the fur color, another string for the breed, and another character string for the noise that it makes. And in fact, I'm going to predefine the noise, initiate it or instantiate it with a value of woof with an exclamation point. So now I'm going to define the setters. So these are the methods that are used to actually set the attributes. So I have a public method that sets the name. It accepts a value of a string called n, and then it assigns the attribute name that value. And then I've got similarly another setter for set fur color, another setter for set breed. Notice that all of these mutator methods are public. So I can't directly change the strings for the name and fur color and breed. I've actually restricted it so the only way I can change the name, fur color, and breed is by using those predefined public methods, set name, set fur color, and set breed. And I'll give you an example of some of that later. The third section on the top right is in red. These are your accessors. So the purple ones are the mutators, and these are your accessors. And I've named them get name, get fur color, and bark. And these are also public. And because they're expected to return a string, that's why it says that it's a public string, and then I'm naming the function get name. In the parentheses, there's nothing there because it's not expecting you to type in anything. When you tell the computer you want to get the name of the dog, it will return the name of the dog. And the same thing for the fur color. And bark is interesting because bark is not really a getter. It's a different type of method. It's not an accessor or a mutator. It just does something. So in this case, public void bark will instruct the computer program to go to the terminal screen and print out a variable, whatever variable is assigned to the name noise. So that's what that system out print line shorthand does in Java. So this example covers a lot of useful things. First, it covers inheritance. Notice that the dog class extends the mammal class. It covers encapsulation. All of my attributes are private, but I've made sure that at least for the ones I want people to be able to manipulate, I've created accessors and mutators for them, my getters and setters. It demonstrates composition in sort of a roundabout way. You'll notice that the word string is capitalized, and that's because in Java, even a character string is actually a type of object, and that's because the class of string, you can do things to it. It has its own attributes and methods, like the length of the string, and you can reverse it and uppercase it and lowercase it and things like that. So I didn't have to tell the computer how to do all that. It thankfully already has in the system classes the string class. And last is polymorphism. That let's say we wanted to create a subclass of dog that extends another subclass that extends the dog class. It doesn't have to say woof. It can say whatever it wants. It could actually override that last attribute there. So that previous screen was just the class. It doesn't do anything by itself. It simply defines the blueprint of a dog. This screen is the actual computer program that does something with that blueprint. In Java, that crazy string at the front, public static void main strings brackets args, ARG, basically tells the computer, all right, listen, we're about to do some Java, we're about to execute a Java program, pay attention. And the first instruction that I'm passing in the program is this capital dog, my dog equals new dog. It's probably a very funny sentence to look at if you're not familiar with these object-oriented programming languages or Java, but that basically says, listen, I want to create a new member of the class dog, and I'm going to call it my dog. In order to do that, I'm going to instantiate a member of the dog class, and I'm not going to pass any arguments. I'm just going to say a new dog. Now, the first thing I want to do, which is the next line, is to change the name of this dog. And remember, I can't just say mydog.name equals something because it's a private string. I can't access it directly. I have to go through the setName mutator. And by convention in these object-oriented programming languages, all of the attributes and methods of a specific class can be accessed by simply typing a period after the name of the class, and then you can type in the attribute or method. So if I want to access the setName method of the myDog class or the myDog object, I would say mydog.setName, and remember it's expecting a string, so I can type in Amia with quotes around it. And I can do the same thing for fur color. It's also expecting a string, so mydog.setFurColor parentheses brown. Now I'm going to go to the screen and I'm going to tell the computer to do something on the terminal. I'm going to compose this sentence, my dog's name is, and then I'm going to concatenate this variable, mydog.getName. And just like I couldn't access the name attribute directly, I have to use the getters and setters. That's why I'm using the getName method here to actually pull the dog's name. And then the last instruction in this computer program is mydog.bark, and then the computer program ends. So if you've been following along, and hopefully if you have had some prior experience with these programming languages, you should be able to see that what this program does is it first creates a member of the dog class called myDog. It sets the name to Amia, it sets the fur color to brown. Then it says my dog's name is, and because we had just set the name to Amia, it should say my dog's name is Amia. And then try to guess what it'll say when you execute the mydog.bark statement. You'll remember that from the actual template for the class itself, that bark function actually returns a value of woof. And we didn't override it, so it has no reason to show anything but woof. So it'll say, my dog's name is Amia, woof. Now this pretty trivial example actually demonstrates a lot of useful things. First is instantiation, which is that it shows you how you create a new member of the class dog. It shows mutators, all of those, the setters, the set name, Amia, and set fur color brown, are us accessing that's a bad choice of words, us using the mutators to actually manipulate those attributes. And then it has the accessor for get name. We use that in order to create that sentence at the very end, such that it returns the actual name of this dog. All right, so switching gears from object-oriented programming, let's talk about data. There are many different types of data. We're going to start by, I like to think of these as almost like a hierarchy of data, as going up from qualitative up to quantitative data. The simplest type of data you can think of are something called nominal data. And we can think of these as categorical, or basically data with names. And when you think of the word nominal, you should think of names. By definition, nominal data are data that are mutually exclusive categories. They're unordered. There's no implied order. They are discrete, and they may represent things, in our world, things like patient smoking status, never smoked, former smoker, heavy smoker, and so on and so forth. The only type of statistical calculation you can do on nominal data is to calculate the mode, the most frequently occurring value. That's the only measure of central tendency you can do on nominal data. Other examples of nominal data might be, for example, the sex of the patient, or zip code data, or something like that. One step up the sort of data hierarchy are ordinal data. And you can think of these as nominal data, but ones where there's an implied order. And that can be a natural or can be sort of assumed order. So for example, t-shirt sizes, small, medium, and large. That's an example of, yes, those are names for categories, but there's an implied order that large is bigger than medium, which is bigger than small. Asthma severity is a type of ordinal data. Intermittent versus mild persistent versus moderate persistent versus severe persistent. You're kind of going up a scale. Likert scales of patient satisfaction, pain scales. These are all examples of ordinal data where higher represents something different than lower on the scale. Because we've now implied an order, you can do something else with ordinal data that you couldn't do with nominal data. We can still do the mode, the most frequently occurring value, but now we can also measure the median, the middle ranked value, because now there is an order and therefore there is a middle value. Now we get into quantitative data. So we went from nominal to ordinal, and now we're going to interval data. This is where there's not only just an implied order, but the intervals between the categories actually represent the same or the equivalent distance. And an example of this might be a calendar year, where the difference between 1997 and 1998 is the same amount of time as the difference between 2000 and 2001. Temperature is a good example of an interval type of data. So, for example, the difference between 32 degrees Fahrenheit and 33 degrees Fahrenheit represents the same amount of heat, the same quantity of heat as the difference between 76 and 77 degrees of Fahrenheit. Because of this, because the intervals mean something, you can do not just the mode and not just the median, but now you can actually take the average, the arithmetic mean, as the measure of central tendency. One type of data that's slightly more rigorous than interval data is ratio data. And the key difference here is that with ratio data, 0 means something, and it's not arbitrarily chosen. So think about, for example, the difference between the Fahrenheit scale and the Kelvin scale. If you remember from chemistry and physics, 0 Kelvin actually means absolute zero. It is the absence of heat. And so in the Kelvin scale, we can say that the Kelvin scale is a type of ratio data. 0 Fahrenheit does not mean that. 0 Fahrenheit does not mean the absence of all heat. And so Fahrenheit is an interval scale, but Kelvin is a ratio scale. Other examples of ratio data are things like area. An object can have 0 surface area. distance is a ratio. You can travel zero distance. But in contrast, year zero does not mean the beginning of time, and therefore year is not a ratio timescale. Because of this idea of zero meaning something, you can now do what's called the geometric mean. And I don't think I've actually ever done this in any intentional way. But in addition to the mode, the median, the arithmetic mean, and now you can do the geometric mean, which is the nth root of the product of all n values among the set of data. These differences between the different types of data are useful when we think about data transformations. When you go from when you transform data, you're basically changing it from one data type to another, usually intentionally. And you should be aware of what happens to that data when you make that transformation. So, for example, when you switch from interval to ratio data, there might be a useful reason to do that. Let's say that in one part of your software system or a simple spreadsheet, you're storing the value for the actual calendar year that a patient was diagnosed with cancer. That's an interval. Again, because year zero does not mean the beginning of time. It might be useful to store it as a ratio, depending on what kind of analytic purpose that you want the data to serve. And it would be straightforward to convert the year that a patient was diagnosed with cancer to the number of years since diagnosis. Today's date minus the year of diagnosis. And now that becomes a ratio because a zero in that construct does mean 0 years have elapsed, 0 time has elapsed since the diagnosis of cancer. Other types of data transformation, you don't necessarily have to transform between data types. You can keep it the same, but you might lose or gain a resolution or some data integrity. So, for example, you can transform data from one interval to another, or from one ratio to another. And the most common example of this is something like image processing. If I take a giant picture and I simply downscale it, if I simply sample it in such a way so it's half as long and half as wide, I'm still storing the same type of data, but now it takes up half as much memory. But I've also lost much of the data in doing that. So when you do these conversions, you have to be aware of sort of do you lose data or not. Another example of a data transformation that has a very specific name is when you transform from an interval to ordinal data. And the name of this technique is called binning, commonly in the social sciences. It's very useful. For example, let's say I have a continuous variable like age, but I want to group them into useful categories for the purposes of analysis. I can use this to smooth out the effects of minor observation errors or to basically help make sense of the data I'm looking at. So I might take age in years, but then group the patients according to their age into useful bins, such as neonate, infant, toddler, child, adolescent, adult, etc. And again, this is ordinal data because there's an implied order, at least in the example that I've chosen here. And I can't reinforce this enough, but be aware of what you gain or lose when you transform data. When you compress an image or an audio file and you downsample, you can lose data. When you bin continuous data into ordinal buckets, you lose data. If you didn't save the original interval data and you've now only saved the categorical or ordinal data, you can't go back. Now, we can organize these data into different types of data structures, and the most simple kinds are these Boolean, what are called primitive types. So Boolean values of true or false, 1 or 0, yes or no, are a very primitive data structure, often called a Boolean variable. We've talked about character strings, often called CHARs or CHARs. When you represent numbers, you can choose how precise and how long you want the variable to be. In other words, how long the largest number is. These can be floating point numbers or double precision numbers. Another type of primitive is an integer, often called an int, int. If we have a collection of multiple primitives, we can actually organize them into arrays and composite structures. So, for example, an array is basically a collection of elements identified by their position and their key in their index. So take a look at this example here. I'm going to create a variable. I think this example is in JavaScript called precedence, and this precedence variable is actually an array, and it contains 5 different character strings: Washington, Adams, Jefferson, Madison, and Monroe in order. I can actually access some of the methods, or I can describe this array by checking the length of it, and I would do that by saying precedence.length, and that would return the value of 5 in our example. Then I can access individual elements of the array according to their index, and at least in this computer programming language, the first position is represented by the 0th index. So the indexes in this example go from 0 to n-1, or 0 to 4. And so if I want to access that first position of Washington, I would say precedence bracket 0, and that would represent the variable Washington. Now, this is a collection of strings, but there's no reason why you can't have a collection of collections, and that's called a multi-dimensional array. Imagine we have a whole set of arrays that are nested in other arrays and more complex data structures, and you can see that you can come up with these very portable ways to represent very, very complicated concepts, like an entire patient record, for example. We talked about strings as being a specific data type in many computer programming languages because they have methods and attributes associated with them. So I call them out separately here from simple character values. And then dates. Dates are actually really problematic in computer languages, as any of us who've had to deal with daylight savings time in our electronic health records have probably realized. Most programming languages have very special ways to deal with dates, and it's precisely because of this issue of time zones and daylight savings time and leap year, and whether you're using the Gregorian calendar or some other type of calendar. And while you could store a date, for example, in a relational database management system, that's what RDBMS stands for. While you could store a date as a character string, the problem with that strategy is that it really, really limits what you can do with it afterwards. And this is like one of my pet peeves. You probably all had to deal with somebody giving you an Excel spreadsheet where all the dates are represented as character strings, and then you can't do any math with those. You can't compare dates. You can't measure the time elapsed between dates and things like that. So, for example, in a piece of Oracle SQL code, someone might define a column type of variable length character string, or varchar, and then they would store a character value of 01/13/12 to represent January the 13th, 2012. But now that it's a character string, I literally can't do anything useful with that in terms of manipulating it as a date. So the preferred way to do it is to define that column as a date and actually store the value as a date. Time is also a type of data structure that has often complex ways to represent it in computer programming languages. I think you deserve a computer programming joke. Anyone know what this is on the screen? This is a hip hip array. I didn't say the jokes were going to be any good. All right, now let's talk about control structures. A control structure in a programming language is a way to instruct the computer where to go in the flow, basically where it's supposed to be and where it's supposed to go next. The most primitive control structures we have are basically labels like line numbers and go-to statements that basically instruct the program to go from one part of the code to another part. And then if it's a subroutine and the expectation is that you're supposed to come back to the starting point, you can do something called go sub. That might be the label that's used in that language. You can go do some stuff and then come back when you call the return, when you type the return statement. But you can only do so much with labels and linear sequences and go-tos and go subs. The more powerful control structures are things like choice statements. This is where you tell the computer if certain variables match a certain condition, then you can do something. So, for example, some of the most common choice structures are if, then, else, and case, when. If, then, else, this is an example of one. So I'm saying if the age of the patient is greater than 12 and the sex equals female, and notice the double ampersand here is how, in this computer programming language, we're representing the and Boolean operator. So if that first statement, age greater than 12, is true, and the second statement, sex equals female, is true, then show the pregnancy risk warning, or else do something or do nothing. Notice that the part between the if and the then should return a Boolean. In other words, it has to be written in such a way that it either returns true or false, and that's why I phrased it in that very specific way. It's the conjunction operator of those two statements. The other example is case when. So in our first example, we just had this one condition we needed to satisfy, the age and sex. But maybe there's a lot of conditions I need to parse through. And rather than doing a lot of what called nested if-then statements, where at the else phrase I could do another if-then, an easier way to represent these multiple cases is to actually use the case when control structure. And here's an example. And you can read this as, in the case when age is less than 8, do something. And in the case when the age is between 8 and 60, do something else. And in the case when the age is greater than 60, do something else. So I basically defined 3 branch points using this one set of structures. Another very common control structure is a loop structure. And this is when I want the computer to do something more than once, but for a very specific number of times. There are 3 types of loop structures that you should know. First is called the count-controlled loop structure with an iterator. The example of this is the for next loop. The second one is the condition-controlled loop, which is called the while loop. And the third one is called the collection-controlled loop. The example of the name for that is a for each in loop. So a for each statement, or a while statement, or a for next statement. Let's look at the first one, the for next statement. Notice that this one has a counter built into it, or what's called an iterator. So I'm saying for as long as that counter statement is true, do something. And the counter statement has to include the initial parameter for the iterator. I'm saying I is equal to 1. The final parameter for the iterator, in this case I is less than 20. And then how I want the computer to count through them. In this case, after every loop, I is equal to the previous I plus 1. So for I equals 1, I less than 20, I equals I plus 1, do something. And you can imagine that that would actually just do the thing that you asked the computer to do 20 times. I could represent the exact same thing using a while loop. So I can say while I is less than 20, do something, and then at the end of that something, add 1 to I. And notice that both of those things will accomplish the same thing. They're semantically equivalent, although there's slightly different ways of phrasing the loop itself. Maybe I don't want to count the number of times to do it. I just want the computer to perform the same step as many times as I need it to. And in that case, you might need something like a collection-controlled loop. In this case, for each in. So let's say I have an array of patients, each identified by their first name, like John, Martha, Alice, and Carlos. And I'll say, for each variable I in the patient's array, do something. So it'll look at the first I, which is the 0 index position of patients, or John, and then it'll do something to John. Then it'll do something to Martha. Then it'll do it to Alice and do it to Carlos. Maybe we're trying to batch register a bunch of patients that are coming into the clinic tomorrow or something. So this is the type of control structure you might use for that. Now I'm going to take you way back to like 1982 when I was a elementary school kid, and we're going to talk about Apple Basic. The reason why I like Apple Basic for this example is because it's a great example of a procedural language, and it has some very nice, easy to follow examples of control structures. You're not going to obviously have to know Apple Basic for the exam, but if you can read through this set of code, these 10 or 11 instructions, and if you can understand what the program is doing, then I think you're going to be in good shape for those control structures. So notice that these are numeric labels, which is one tip off that this is a procedural language. And line 10, which is the first line of the program, says for t equals 1 to 10. So you can already tell that I'm going to set up a for next loop. Line 20 is this phrase home : HGR. And you obviously don't have to know what this means, but in Apple Basic, this was really cool. This would clear the screen, the home screen, and it would put it into high resolution graphics mode, HGR. And in line 30, I'm going to say for n equals 1 to 100. And you might be thinking, wait a minute, we didn't do anything with that t loop. And that's because this is a nested for next loop. In other words, we've now created a loop inside of a loop. We haven't closed the t loop yet, and we've created the n loop within it. And this one's even bigger. This is for n equals 1 to 100. So something's going to happen 100 times, and then something on the outside is going to happen 10 times. Line 40 and 50 and 60, I'm going to define three variables. The first one in line 40 is variable x, and you don't necessarily have to know how this is done or what this string means, but in Apple Basic, the random function rnd picks a number between 0 and 1, and I'm multiplying by 280, and I'm rounding it to the nearest integer. So this basically picks an integer between 1 and 280. The next one does between 1 and 192, and the next one does between 1 and 7. And those are significant because 280 and 192 are the x and y dimensions of high-res graphics mode. It's the maximum resolution in the x and y axis of that screen. So by today's standards, not that high-res, but high-res enough for 1982 and enough to keep this 12-year-old kid busy back then. And then the last one, C, the significance of that 7 is that there were 7 colors you could work with in high-res graphics mode. So I've picked an XY coordinate using those two random number generators in lines 40 and 50, and I've picked a random color for my plotter using that line in 60. And in line 70 and 80 is when we start using those variables. So I'm going to say H color equals C, which means the high-res plotter color will be assigned to the number from line 60. And then I'm going to plot a line that starts at the first point and extends to the second point. So 280 divided by 2, comma 192 divided by 2. That's an XY coordinate. And for those of you that are following along, you'll recognize that that's the exact middle of the screen. I've taken the X dimension and the Y dimension of the screen and I've divided by 2. So that's the center of the X-axis and the center of the Y-axis on this screen. And then that line is going to start at the center of the screen. It'll go all the way to the XY values that we picked in line 40 and line 50. And finally, we get to the closure of our next loop. So in line 90, it says next n, which means it'll pop back to line 30. It'll iterate to number 2. It'll pick another set of X, Y, and C, plot another line, and then do it again. Each time a different line of random length and random color, but always starting in the center. And when it does that 100 times, then it'll exit the n loop and it'll go to line 100, where it does the t loop. And remember, that'll take us all the way back to line 10. We'll now advance to the t will now be equal to 2. It'll clear the screen, go to high-res graphics mode, and do it all over again. So, what does this program do? Well, it draws a cool starburst pattern. In fact, the starburst will contain 100 rays of different lengths and colors, always starting in the center of the screen. And each time, after it's finished drawing the 100 lines, it'll clear the screen and do it again. And it'll draw a total of 10 starbursts before it finally finishes and exits. And here is what that awesome high-res graphics mode in Apple Basic looks like. This is one of the complete end loops in that structure. And imagine it does this 10 times, each time drawing a different starburst. This was like the epitome of cool when I was a kid. And you can imagine I was probably a pretty cool kid if I was programming in Apple Basic. So if you want to really mess around with Apple Basic, there actually are these readily available Apple Basic emulators online. I've linked to one of these here. Although you can find them just by using your search engine. And I would encourage you to actually type in that program and see what happens. And as an exercise for you, how would you modify the program such that the center of the starburst is also randomly generated, not always at the center of the screen? And I'll leave that as a challenge for you. So that last example, is exactly 11 lines long. It wasn't that complicated. In fact, we could follow it in our heads and not have to do a whole lot of head scratching. But you can imagine that most computer programs are not that easy and require a lot more thought and tracking of variable values. When you start writing anything but the most trivial of computer programs, you probably want to first kind of plan out your algorithm, plan out the structure of your program, articulate in human language or near human language, like what you want the program to do in what sequence. And to do this, people often use, there actually is a formal standard for this called pseudocode. We're not going to learn the formal standard. We're going to learn kind of the way pseudocode started, which is basically a shorthand way to describe what you want the program to do without worrying about the semantic specifics of which programming language. In other words, before I get to the point of actually coding it in Java or Visual Basic.net or whatever, I want to sketch out what the program's doing, and I want to be able to convey it in a way that any other programmer can pick it up and look at it and understand it. Okay? So that's what pseudocode is. And then I may want to actually imagine what would happen if I ran that pseudocode by passing different variables to it and seeing what the state of the variables is at each step in the process. To do that is something called, you have to use something called a trace table, and we'll give an example of that as well. So back in pseudocode, you want to use normal English expressions to represent all those common computer functions like variable assignment, control and loop structures, logic functions, and if you're dealing with databases, your inputs and outputs and other database functions. And this is a summary, but the goal is to represent an algorithm in a way that it can be implemented in any computer program simply to convey the program flow and the logic. And again, it's also a good way to check your algorithm before you start coding so you don't waste time once you get to the console. So here's some pseudocode on the left. This is in a procedural language. I've got 9 lines of code, and I'm going to create a trace table on the right to describe what this program does line by line. So just let's look at the program first. So it's x equals 10, y equals 2, print x plus y. The next line is print x divided by y. Then I'm going to do a for next loop for I equals 1 to 3, x equals x minus 1, print x, and then go to the next I, and then finally print I love Amia. So you might be able to figure this out in your head. And in fact, if you sort of stare at it enough, hopefully you'll be able to get it. But for the sake of actually filling out this trace table, let's do it step by step. In line 1, I'm going to fill in the first row of my trace table. I'm going to say I'm at line 1, and all I've done is I've assigned the value of 10 to the variable x. By the way, in the trace table, you'll see that each of the columns represents all of the variables in my program, whether or not they've been used yet or not at that point in the program. And then I've created a separate column for the actual output of the program on the screen. Now by line 2, I've defined y. Notice the value of x has not changed. So x is still equal to 10 and y is equal to 2. At line 3, x is still 10, y is 2, but now I've output the number 12 on the console because that's what the statement's asking us to do. And so on and so forth. Line 4 on the screen will print the number 5. That's x divided by y. Line 5 doesn't do anything at the console, but it now adds a value for the iterator I. So now I is starting out with its initial value of 1. Line 6, I'm taking x from the previous statement and I'm subtracting 1. So now that's why I've listed x equals 9, y equals 2, and I equals 1. Line 7, it's still 9, 2, and 1, but now I'm printing the value of x on the output. And then line 8, I'm going to the next iteration of I. So I skip all the way back. I advance I by 1, so now I is equal to 2. And I skip back to the line after my for next statement, which is line 6. So I go from line 8 to line 6. Now I subtract 1 from x again, so x is equal to 8, Y is 2, I is still 2. I go to line 7, where I'm going to print that number 8 on the screen. I go to 8 again. This time I iterate to the next value of I. So now I is equal to 3. And I'll jump back to 6. Subtract 1 from x again. So now x is equal to 7. Y is still equal to 2. I is still equal to 3. Line 7 asks me to print that value. So now it'll print the number 7 on the screen. And now I've run out of x's. I've reached the last... I've run out of i's. I've reached the last number in my iterator. I remember in line 5, I only goes up to 3, and I is equal to 3 here. So that tells the computer we can exit this for next loop. So then it jumps to line 9, because there is no next I, and it prints I love Amia. So the final output of this 9 lines of code is the number 12, 5, 9, 8, 7, I love Amia. Now, the significance of this for the exam is that you may be expected to look at a piece of pseudocode and be able to trace the value of a specific variable. And so they might show you some code. They might show you half or blank trace table and say, at the end of this computer program, what's the value of y, or something like that. So you should be able to do this exercise with whatever code they give you. And obviously, with time limitations in the exam, they're not going to give you some crazy thing. They're going to give you a short example that you can do probably in a minute or two. And so be prepared to fill out your trace table. Here's where I actually will show you the loops. So the first loop is indicated in 6, 7, and 8. There's the next loop there where I is equal to 2, and there's the final loop until we exit and done. Okay, here's a more complicated example, and if you can understand step by step this example, if you can do the trace table on this example and figure out what it's doing, then I think you'll be in good shape for the exam. And I've made this intentionally tricky and intentionally hard because I want you guys to spend some time looking at this. So here's the pseudocode example. Let n equals 2. While n is less than 10, do the following. First, set the value of a variable t to be true. And now I'm going to do another loop. Let I equals 2, and for every number where I is less than n, do all this stuff that's listed in line 5. And then, I'll go through it actually. So it says if the output of this mathematical function n mod I is not equal to 0, then increase I by 1. Line 6, if that's not true, if line 5 is not true, then set the value of t equal to false and exit the loop. Line 7, now I've gone through all of my i's. If t is still true, then print the number n. In line 8, increase n by 1. So I've intentionally made this an example that you probably can't do easily in your head. And I'm using a specific function that you should be aware of called the modulo function. That's what that n mod I instruction is in line 5. Now, you may be asking, what is the modulo function? Well, the modulo function is kind of like the division function, but not really. So the modulo function returns the remainder when you divide two numbers. So 3 mod 2 equals 1 because 2 goes into 3 once with a remainder of 1. 23 mod 12 equals 11 because 12 goes into 23 not quite twice, it goes into it only once, and then the remainder is 11. 17 mod 12 is equal to 5. 13 mod 5 equals 3, and those are, I've given the examples there. And even if you think you've never done modulo math before, I guarantee you have, because when you convert from military time to standard time, you're basically using modulo math. So when someone says an event is going to take place at 2300 and you think, oh, that's 11 p.m., the reason you know that is because 23 mod 12 is equal to 11. Ditto for when something happens at 1700 in military time, that's 5 p.m. So with that definition of the modulo function, the way I've just described it, let's make a trace table for this program. And there's two questions here. The first one is, how many numbers will this output on the screen? And the second question for you is, what do these numbers have in common? Okay, so hopefully you took some time to create a trace table for that previous example and tried to work through it. Yours may not match mine exactly, but I've listed one here for your reference. So I created a table that included not just the variables n and I and t and the output, but also I created two special columns for the conditions that I want to track, namely whether or not n is less than 10, which is the condition in line 2, and whether or not I is less than n, which is the condition in line 4, because I have a control structure there for every number where I is less than n, do something. I also wanted to track this value n mod I for reasons that will become apparent a little bit later. So if you follow this example, basically I start with n equal to 2. Initially it asks if n is less than 10, so which is true. So t gets gets assigned to the value true. And now I is equal to 2. We're on line 4. But I is not less than n because now they're both equal to 2. So that statement for every number I less than n, that's not a true statement. There is no number between I and n where I is less than n. So you can skip line 5 and skip line 6 and basically exit that for next loop. And now at line 7, if t is still true, which it is, we didn't change the variable value of t, then we print the value of n. So that's why in the second line of my trace table, after all that, the output is 2. Now, I'll leave it to you to figure out what happens with all the other iterations of n, but look at the pattern that's generated on the output line and see what they have in common. Notice that the numbers here are 2, 3, 5, and 7. And the spaces between them are getting larger and larger. What this program is actually doing is it's printing all the prime numbers less than 10. It's the prime numbers less than 10 because we're only doing this as long as n is less than 10 in line 2. And we know it's the prime numbers because of this modulo statement. And so think about what it means if n mod I is equal to 0. That means that n is evenly divisible. That means n is evenly divisible by I with no remainder. And if it's divisible by something, then it's not prime, right? So the fact that 6 is divisible by 3 means that 6 is not a prime number. But what I'm checking in lines 4, 5, and 6 is for every number between 2 and n, if the remainder is not 0, then check the next number. And if you can satisfy that for every single number all the way up to n, then you know this number is prime. So for example, when we get to 7, where n is equal to 7, we're saying, okay, is 7 divisible evenly by 2? Nope. Okay, what about 3? No. What about 4? No. What about 5? No. What about 6? No. So now we've tested all the numbers between 2 and 7, and none of them returned n mod I equals 0, and therefore we know that 7 is prime. So this is a painstaking way to check for primeness, but it works. And in fact, there's some simple modifications you can do to this. If you wanted to calculate all the prime numbers up to 100, what would you have to do? You'd have to change the statement in line 2 and say, while n is less than 100, do the following. So this is our pseudocode version. And if you want to test this out, I'll show you on the next slide. If any of you want to get your hands dirty with JavaScript, there are online JavaScript interpreters. So basically on the left half of the screen, it'll show you a console where you can type in your JavaScript code. It'll actually even format your nested loops and show these little drop bars to show you where the loops start and end. And on the right side, when you hit run, it'll actually show you what the console would show in a JavaScript output. The tool that I've used for this is a website called repl.it, R-E-P-L.it, which is, again, a web browser-based JavaScript console where you can test your code. And what you should be able to see is that the code that I've listed here in those 15 lines is the exact JavaScript version of the pseudocode that we had on the previous screen. And the only funky parts in here are in lines 3 and 4. Specifically, JavaScript has what's called a ternary operator, or a funny way of showing those for next loops. So I have for I equals 2, semicolon, I less than n, semicolon, I plus plus. I plus plus is a shorthand way in JavaScript to actually add 1 to the value of I. And then in JavaScript, the modulo function is represented by the percent sign. So if n percent sign I, and remember from like 30 slides ago, I said that the exclamation point in many programming languages is the negation operator, and the equals that bit of code, the equals operator in JavaScript is the assignment operator, or sorry, it's the Boolean comparison operator. So I'm saying if n mod I is not equal to 0, then do the stuff in the next part of the loop. So both of those statements in line 3 and in line 4 are the JavaScript versions of the pseudocode that we had on the previous screen. And you can see that on the output console, it actually does print the numbers 2, 3, 5, 7, and then it stops. Again, as a bonus to you, what would I have to change in this screen, in the JavaScript screen, to print all the prime numbers less than 100? The answer is that in line 1, when we have that funny 3-part construct for defining our for next loop, just like we have in line 3, you change that number from n is less than 10 to n is less than 100. And here I've listed all the hints for those of you that are not familiar with JavaScript for how to understand what this represents. For the purposes of the test, you're not expected to know JavaScript. My guess is they will not show you something like this left half of the screen because you're not expected to know any specific programming language. The only exception to that is you may be expected to know some SQL, and we're going to cover that in a different lecture. But imagine they showed you the pseudocode version of this. You would be expected to know how to do the trace table for that. Also, in one of the live classes, students asked me what's the difference between a trace table and a truth table. The trace table is how you follow a computer program through stepwise. A truth table goes back to the lecture when we were talking about how to guess the output of those logic gates. So programming questions on the exam, what can you expect? Well, you will be expected to interpret a pseudocode algorithm and predict the output. But again, it's got to be simple enough that you can do it in a couple minutes because you don't have 10 minutes to spend on a single question on this exam. You will be expected to understand control structures and loops and operators and variable assignment. You will be expected to complete a truth table. You can expect to see a trace table. You're not likely to be tested on any specific language except for SQL. And if you are tested on a real computer programming language, I guarantee you that it will be one of the higher level programming languages that is basically like looking at English. So you can just treat it like pseudocode for the purposes of the question. All right. My guess is you're probably ready for another computer programming joke. So here it is. A programmer goes to the store. His wife says, buy a gallon of milk, and if they have eggs, buy a dozen. The programmer comes back with 13 gallons of milk. Believe it or not, this is actually a very useful computer programming joke because It references something called variable scope. So in this example, where the wife says if they have eggs by a dozen, it's unclear what the scope of the value of a dozen is. Does the scope refer to the eggs, or does the scope refer to the milk? And so this computer programmer, who's our literalist, thought it still applied to the gallon of milk, and that's what he did. Computer humor, you gotta love it. Let's talk about a specific type of algorithm or specific type of function called a hash function. So what hash functions have in common is that they are algorithms that can map data of any arbitrary length to data of a very specific fixed length. And so these are basically examples of binning functions. They're ways that you can assign, basically map large chunks of data to more simplified values or representations. And the thing that gets returned, the return value, is often known as a hash value, a hash code, a hash sum, or something called a checksum. And you might be thinking, well, why is this useful? Why do I want to take a giant string of useful text and return an arbitrary an arbitrary string of numeric numbers or hexadecimal or something like that? And it's because these are often used in data integrity checking. So there's a common function, for example, called the MD5 hash, which I think returns like a 32-bit character or something like that. And if I took the MD5 hash of a giant file, a piece of software that I downloaded, and I compared it to what the programmer told me, the developer told me the MD5 hash was supposed to be, I could be fairly reassured that the version I downloaded matches the programmer's version. In other words, it was not corrupted during the download. It had not been tampered with by somebody else. In contrast, if I download it and I run the MD5 hash on my local computer and it's not the same as the MD5 hash that the developer told me to expect, then I would not try to install that software because it might be that the software has been corrupted. Another checksum or hash function that many of you are probably familiar with or you've used and you didn't even know it is at the end of the National Provider Identifier, your NPI number. So the last digit in the NPI number is actually calculated or derived from the previous digits using something called the Luhn algorithm, L-U-H-N. And as you can imagine, the values of that last digit are only between 0 and 9. They're any one of the digits between 0 and 9. So that's, I think, a more concrete example of how it's a binning function. It takes your entire NPI number, and based on what the NPI number is, it either gives it a value of 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Now, this isn't so useful in terms of like cryptography or something like that. And it certainly doesn't prevent someone from trying to make up an NPI number, especially because the Luhn algorithm is published. But the reason why it's useful is that if you're typing the NPI number into a computer program, this is a way for the computer program to quickly check whether or not this is even a valid NPI number. So it's meant to protect against keystroke errors, that somebody fat-fingered a number as they're typing it in. There's only a 1 in 10 chance that they could randomly do so and still come up with the same checksum. So notice that it doesn't eliminate keystroke errors, it just reduces the likelihood of them, roughly tenfold. Here's an example of why the MD5 hash specifically is so useful in data integrity checking. I'm taking this string of text. The patient has evidence of hypertrophy, and imagine this is part of like an input into some system. And I take the MD5 hash of that, and it returns this hexadecimal string starting with 65 DC. And notice that if I do the exact same MD5 on a very slightly different text string represented, all I've changed is that first ASCII character from a capital T to a lowercase t. This function is so sensitive to those changes that now I end up with a vastly different MD5 hash. What are other ways that hash functions are useful? Well, they're useful in cryptography. Specifically, if you're writing a computer program that has anything to do with usernames and passwords, it is a best practice to not store the password itself, but rather to store a hashed version of the password. And the reason is if someone ever gets access to your computer program or your system, your database, you don't want them to have a list of unhashed or unencrypted passwords. So you might think, well, if you hash my password, how can you tell if I've typed in the right password or not? And that's because that these computer programs actually are comparing the hashes, not the actual passwords. As a rule of thumb, and you've probably seen these systems, although I think they're less and less common these days, if you ever go to a website that makes you register for a username and password, and then later you have to reset that password, if they send you your password in plain text, unencrypted, that means they're probably either storing them in an unencrypted way, which is a complete no-no, or they're storing them with a reversible function, a reversible hash function, which is also not recommended. Hash functions are also useful in indexing, like when you're indexing a database. And I think this deserves a little bit of explanation. Imagine, for example, I'm looking at a database that contains all the patients in my electronic health record. And if at some point I want to query that list of patients to find a very specific patient named Desai, I would have to theoretically look through every single name in the list. That's the maximum amount of time that it would take would be to actually compare every single value in that list to find the patients with that name. And that can be very cumbersome, especially if you have millions and millions or billions of patients in your database. So we need a mechanism whereby I can basically instruct the computer to take a shortcut. I can quickly point it to a subset of the data that's likely to have the value that it's looking for. So a very simple hash function might be something like take the patient's last name and truncate all but the first character of the name, right? So the hashed function of my name might just be the letter D for Desai. And every patient name that has a Roman alphabet name would match one of these would fit into one of these hash buckets. And because there's only 26 letters in the alphabet, there's only 26 buckets, which means now if I'm trying to look for a specific patient and I've indexed my database with this new hash function, I've reduced the time that it would take to find the correct name theoretically 26-fold. Now, it's not exactly 26-fold because, patient last names are not distributed equally across the alphabet, but you get the idea that an easy hash function might be to actually, alongside the patient's first and last name, to store the hash of their last name, which in this case is basically the first character of their last name. And then when you go look for the patient, you can index it such that you're looking specifically for the hash, only the subset of the data where the hash matches. So theoretically, again, retrieving information is faster since the program only has to look in that one bucket. Let's change gears and talk about software development methodologies. So this is how you organize large software projects, and these are collectively called the Software Development Lifecycle, or SDLC. The reason why you need software development lifecycles or software development methodologies is because, except for the most trivial examples, you need a standard approach for building large programs that start with determining the scope of the program, what it's actually supposed to do. That includes how you're going to organize the programming tasks. This chunk of code is going to be responsible for dealing with the user interface. This chunk of code deals with the storage in the back end, and so on and so forth. That determines the testing requirements for your software. That allows a program manager or a project manager to manage the resources and the time commitments of all the developers involved, and even the non-developers like the stakeholders and the subject matter experts. And then ultimately, you want to be able to deliver software on a reproducible schedule. So here's the basic phases of the software development life cycle. They all start with a planning phase where you're trying to gather your requirements, determine the scope of the project, and also the priority of the work. So what sequence and which work is most important. Next is the software implementation phase. Now, the note here is that in computer programming, implementation refers to actually implementing the algorithm, like writing the code that does the thing you're expected to do. Typically, we think of implementation as the day you go live, the day you implement the software in production. So there is this sort of semantic collision here. We often call software implementation the actual software development or the design. Then there's testing, and there's two concepts you need to know about testing. There's verification and there's validation. Verification is basically, does the software meet the specification and is the code of high quality? Is it defect-free? In other words, are you building the software right or correctly? Validation is, are you building the right software? In other words, does the software actually meet the customer's expectations, satisfy their needs, and do what it's supposed to do? So you can imagine that the software can be defect-free but not do what the end user wanted. Or that it looks great and it meets all their expectations, except for the fact that it's very buggy and crashes all the time. So you can validate but not verify, and vice versa. Documentation is the phase of software development lifecycle where you actually document. You have to keep a record of how the software was developed, what all those arcane bits of code do, by commenting it so that future developers can actually understand what you're trying to do with your obfuscated code base. You want to be able to document the training needs. You want to document the downtime procedures, and so on and so forth. So documentation is absolutely critical for any future enhancements, for debugging, for maintainability, and so on. Deployment is what we often refer to as implementation. That's the contrast that I had in that second bullet point. And this is the point at which you would install the software, customize it for that specific unit or use case, train the users, and then once it's live, actually evaluate its go live to make sure that everything went off successfully. Typically, we do things like command centers immediately after large deployments so we can keep track of all the immediate defects that are picked up. And then finally, once things stabilize, you move on to maintenance. This is one of the main reasons to do maintenance is because you want to be able to support your users in an ongoing fashion, and you need to be able to have a systematic way to collect ideas for new enhancements or to identify and escalate and fix any new defects that are determined. So that was the example of the basic SDLC principles. There are specific SDLC methodologies, and they differ significantly. The granddaddy or the grandparent of all these is the waterfall methodology. And this is where you basically just do everything stepwise, and you're only allowed to go to the next step once you've completed the previous step. So you do all your requirements gathering. And then when you're done, you go to development. And then when you're done, you go to deployment. And then finally verification, and then finally maintenance. The rigidity of this makes it not that appealing, especially for large like EHR projects. And there's a huge disadvantage, which is that a late breaking requirement can be expensive or prohibitive. So if you're in the implementation phase, you've got developers doing stuff, and then you find out that there's a giant gap in the requirements, it's often too late and costly to go back and fix that. So the vulnerability of this is that you might find some defect that's basically a deal breaker, and you might not know about it until the very end. And of course, that defect was something that should have been identified way early during the requirements phase. So an alternate to the waterfall methodology is the spiral methodology. This is an example of what's called risk-oriented software development. And one example of risk, which I think we probably encounter a lot in electronic health records and in informatics, is that maybe the requirements themselves are poorly understood, that we may not know the minute we start talking to the developers, everything about what we want the application to do or how it works. We just have a broad understanding of what we want it to do. So in risk-oriented software development, or in the spiral methodology, you would break that development lifecycle into smaller efforts, and you would tackle each of these as like sub-projects, each of which has their own little mini waterfall. You would hopefully organize those sub-projects according to the areas of highest risk first. And for each of these, again, you do the traditional phases of looking at your objectives, what your alternatives are, identifying and resolving the risks, develop the deliverables for a specific iteration, verify that they're correct, plan the next cycle, commit to a specific approach, and then go on to the next iteration. The advantage of the spiral methodology is that your highest risk is tackled early on when change is less expensive. And that's a recurring theme in all these SDLCs, is that you want to tackle risk early and not wait till the end. And that desire to iterate rapidly, to engineer out defects early, to adapt to changing specifications has led many software shops to embrace a methodology called Agile. This is when you focus on very small, very frequent loops of programming. Some of the popular Agile variations are extreme programming called XP, and Scrum, which is named after the huddle in rugby. And here you have a mechanism to get repeated feedback and regular feedback from your subject matter experts or the product owner through testing and small iterations, small releases. So you mock up a bit of the software and program it, and you get the response back from the product owner, and then you develop that even further, and you get the response from the product owner. You develop it even more, and so on and so forth. Here's some of the terminology that's used by in the Agile methodology. Specifically the Scrum terminology. There's the product owner, the person who represents all the client requirements. Typically, that's the person who interfaces back to that client committee or whatever. For example, we built an asthma care tool at our institution, and rather than having the programmers interface with the entire asthma care committee who created the pathway and the clinical procedures, we had them nominate one person who happened to be a clinical informaticist, who was the product owner and who could go back and forth between the two groups, help escalate decisions that need to be made and get the answers back to the programmers in a timely fashion. The product owner participates in this action of writing user stories, which are brief statements that capture the who, what, and why of a simple requirement. And then you add those stories to the backlog. So the user story might be, we need to be able to capture the active medication list for every asthmatic, including their escalation plan. We need to be able to print out the action plan for this patient's asthma from within the electronic health record, whether it's in a primary care setting or a specialty care setting or an inpatient hospitalization or even the emergency department, and so on and so forth. They compile these stories of how the system should be used, and they add them to the Agile backlog. The next term is this development team, which is typically 3 to 9 programmers who are cross-functional by design. You want them to be able to trade off various coding tasks, maybe alternate between who's doing testing and who's doing documentation. The next is the Scrum Master, who is the rule enforcer and the remover of impediments. So the Scrum Master's responsibility is to look at what's on the backlog, assign tasks for a given unit of development called a sprint, and make sure that all those tasks get done and completed. And a sprint is this basic iteration, this cycle of development in Agile methodology. It's predefined in duration and scope. So they'll say this week's sprint will include these tasks from the backlog list. And then there's a daily scrum. Every day, the Agile team will meet in the morning. They'll review team by team what happened yesterday, what's intended to happen today, and what any obstacles are. Is it true that we're still on track? If we're behind, then why? And what can we do to get back on track? So the advantage of this is that it's by design, it's meant to be extremely flexible. It assumes that the client will change their requirements, which we frequently do in healthcare, and it's equipped to adapt to those unpredicted challenges. So now you've developed your system, and you're going to start connecting it to things. And now you're at the stage of the software development lifecycle that involves system integration. So this is the process of linking subsystems in your software architecture. Oftentimes it involves not just the software folks, but the hardware folks and even the interface teams. To do system integration well, especially in enterprise healthcare, requires a very strong understanding of standards and requires a strong foundation in these terminologies like HL7 and concepts like web services and an understanding of networking. Think about, for example, what it takes to integrate your patient monitors that are constantly streaming real-time data to some downstream system. That depends on a set of reliable networking standards. That depends on a certain set of software services and messaging standards, whether it's web services or HL7 or whatever. There's lots of different styles of system integration. There's something called vertical integration, which is basically that similar systems are grouped by functions into silos. And whereas all the applications might be integrated within a certain silo, like all of your cardiac systems are interfaced, they may not necessarily be integrated between silos. There is something called the star integration, which is where each system that needs a connection to some other system has its own unique connection. It's unfortunately, this adds a lot of complexity. If you have 10 systems, they all need to be integrated to the other 9. That's a lot of single point integrations that basically increase your likelihood of failure. So another probably more elegant way to do this is called horizontal integration, usually involving something called an enterprise service bus. And in that scenario, every system connects once to the bus, and then the bus has connections to every downstream system. So when you need to swap out a specific system like your dietary system or your pharmacy system, theoretically it's supposed to be much easier. Let's talk about quality assurance and testing. You will recall that when we were talking about SDLC, we mentioned a number of times this notion that identifying defects early on is advantageous. And this is meant to represent just how advantageous it is. The rows here represent where the defect is found, like where in the actual software product the defect is, whether it's in a defect in the requirements phase, a defect in the architecture of the system, or in the actual construction or the programming itself, versus when it was detected. Was it detected during the requirements phase, during the architecture construction? Was it detected during system testing, or was it only detected after it was released? And you'll see that if you identify a requirement defect while you're still in the requirement phase, it might incur 1x cost. But if you don't find that defect until after the system is live, now it's 10 to 100 times more costly. I can think of an example of this where a couple of electronic health record systems ago at my institution, we found on the day of go live that there was a defect in the field for registration staff where the Social Security number was captured. And specifically, it was not programmed to accept empty values, which is a problem for pediatric institutions because newborn babies don't have Social Security numbers. So we had to come up with a workaround, which was to, by convention, come up with some string of numbers, all ones, all zeros, or something like that, to allow people to register patients even without Social Security numbers. But ultimately, that was a defect in the requirements phase. In other words, when they created that set of systems for around registration, they failed to take into account the fact that not all patients have Social Security numbers, and therefore that field should not be mandatory. Of course, these days we probably wouldn't store Social Security numbers. You might try to avoid storing them at all in favor of other identifiers. In the abstract, you may think that software testing in healthcare is not that important. This is a very concrete example that everyone should know about related to a biomedical device, the Therac 25. This was a radiation therapy machine that was in use in the mid-80s, and it was actually responsible, because of a software defect, for 6 accidental overdoses, including 3 patient deaths due to massive radiation. It was accidentally administered by the machine. And it was attributed to a failure to detect something called a race condition. And that's when a certain portion of the software, which is only expecting one set of inputs from other parts of the software, actually gets 2 simultaneous or near simultaneous inputs, and it sort of locks up. In hindsight, there were a lot of problems with this. One of them was the poor design of the error messages itself, which was, I think, largely a function of the sort of the state of software interfaces back at the time. But it basically showed the radiation technologists the word malfunction followed by a number between 1 and 64. And they were expected to look up in an instruction, a user manual, what that code represented. And you can imagine that if we're alert fatigue now, they probably weren't paying a lot of attention to the number that they saw. Maybe they were seeing malfunction codes all the time for various reasons. The other, and probably the more insidious problem with this system was that when it did malfunction and patients actually complained about very, very severe pain and burning, the radiation therapists often didn't believe the patient's complaints. They often felt that this was actually, normal for radiation therapy, and sort of dismissed the patient's concerns. So this is a screenshot of the Therac 25, and don't ask me to describe where they might see the error or what anything on the screen actually represents, but the bottom right is basically where they would issue the commands, and somewhere on the screen they would see that error message. Well, how could that have been prevented? How could that tragedy with the Therac 25 machines have been prevented? Now we get into the details of actual software testing. And there's a lot of different approaches to this. There's static testing, which is you're manually reviewing the code itself, hoping that your human vigilance and your eyesight will permit you to see something like a missing semicolon or a misplaced double quote. There's dynamic testing, which is when now, maybe in a debugging environment, I'm actually starting to pass numeric data and variable data to the program. I'm sort of running small segments of the code in a controlled environment to see what happens, to make sure it works correctly. And then there's the more comprehensive approach of test case development. So within test case based approaches, there's 2 broad categories. There's white box and black box. White box testing assumes you know the inner workings of the program. In other words, I can lift up the hood, I can see the computer code, I can see the variable states, I can see all the inputs and outputs. It's basically like staring at the trace table itself. White box testing of an interface, for example, might involve 2 analysts, one on the sending side, one on the receiving side, staring at their HL7 consoles and confirming whether or not a sent message was actually sent and whether a received message was received. They might even be able to peek into the enterprise bus to see if the bus itself received the message and passed it along correctly. One specific subtype of white box testing is called code coverage. And in this example, the programmer will develop a set of test conditions for every possible scenario, for every variable, for all possible inputs, even the ones that may be nonsensical. So for example, let's say I have a line of code where I say, if the patient's age is less than 12, do something. The code coverage exhaustive approach to testing that line of code would include the scenario where the age is less than 12, where the age is greater than 12, where the age is equal to 12 because maybe they forgot the boundary condition, where the age was null, where the age was accidentally a character string and not a numeric value, where the age was represented as a date and not as an integer, and so on and so forth. So you want to see, did I put in the correct error checking? Did I look at all my boundary conditions? Have I anticipated the kinds of errors that users might make? And that's the value of doing code coverage. And to develop these tests, you can imagine, might take a long, long time. So there are ways you can automate that. You can basically set up a test rig to go through and create the test scenarios, the software testing scenarios for all of your code. In contrast to that really, really detailed sort of peek under the hood approach, there's black box testing. And in black box testing, you're testing the software as if you were an end user who had no awareness of the internal status of the software itself. So for example, I'm testing an order set and I place an order in the order set. The only thing I can see in black box testing is whether the user was able to successfully place the order or not. And then on the pharmacy side, the black box version of that would be, did the order print out on the label printer or whatever. So this is basically a form of specification testing. In other words, I'm saying, at least from the perspective of the user and their stories that I compiled and all the specifications we gathered early on, does the system do what it's supposed to do? But this may be insufficient to capture all the defects. And in fact, most people, when we do specification testing, we probably tend to underestimate the number of ways in which users will misuse or find ways to break the software. And so black box testing has its limitation because you typically come up with test scenarios that represent what they call the happy path, the expected way to use the software. We're less good typically at doing exhaustive black box testing that includes inappropriate ways to use the software or ways to think about how to break the software on purpose. Other terms you might hear are unit testing, integration testing, system testing, and acceptance testing or user acceptance testing. Unit testing is when you're looking, it's an example of white box testing. It often involves code coverage and it's developer driven. So when I gave you the example of having a computer that can automatically create code coverage tests for a segment of code, that's an example of unit testing. Integration testing is also white box, but in this case I'm testing specifically the interfaces or the application programming interfaces. That's what API stands for, and it's also developer driven. System testing, as I mentioned, is black box. This is a form of verification. I'm testing the software to see does it meet the actual documented requirements. And then finally there's user acceptance testing, UAT, or sometimes just acceptance testing. It is also black box. You're now saying, you're asking the users to evaluate and sign off or to validate the software that you've built for them. Beta testing is a limited form of user acceptance testing where you're asking a small group of users to give you rapid input. But as one way to think of it is that beta testers themselves do not often have access to the code, so that's why it's still black box testing. Another common example you hear is something called regression testing. A regression is a new defect that's revealed with the addition of a new functionality. So, let's say, for example, your electronic health record is undergoing an upgrade. And when you complete the upgrade, you notice that everything's working as expected. And then there's some defects that you could have anticipated because they're changing things that you knew they were changing. And then there is a set of defects that are completely out of the blue. They are defects in areas that were not even touched by the upgrade as far as you could tell. That's called a regression. So a software regression is a new defect that's revealed with the addition of new functionality, often in an area that is unrelated to the new functionality. And really the only defense against a regression defect, a software regression, or this type of defect, is to add them to future test cases. So if you know that the last time they messed with the orders screen, that the registration screen broke, then you can add testing of the registration screen to the next set of software tests whenever there's an upgrade to the order screen. So that's the end of the lecture. And thank you for your time. I know this was a long lecture, but again, this is going to be high yield stuff on the exam, and I hope you enjoyed it. There's a lot of suggested additional reading here. If you want some examples and more formal definitions of some of these SDLCs and things like that, Wikipedia is a great resource. I am shamelessly plugging these free resources because I don't think you need to go out and buy a computer textbook for this. But if you do want to dip your toes into computer programming, and if you haven't done much of it before, I would refer you to these learning resources. Specifically, if you want to look at what the pseudocode standard looks like and some examples of mocked up pseudocode, you can look at that first link. That's the link to the second link is the link to the REPL.IT JavaScript console, where you can type in the example from the previous slide where we're looking at the algorithm that looks at primeness, and see if you can modify it and see if you can get it to do something different. And if you want a very broad overview of JavaScript, there's this website w3schools.com, and they actually have tutorials on a lot of different programming languages, but they have a particularly good one on JavaScript that goes through very, very useful sections of interest: syntax, statements, variables, operators, arithmetic assignment, data types, functions, so on and so forth. I would actually take a look at this because the sections on like the loops, switches, control structures are eminently useful and likely to be tested. There's also another YouTube pseudocode tutorial and a very good example of a trace table on YouTube that I would refer all of you to. Thanks again for your time. That's the end of this lecture.